Let's have a look at the last three conditions for the time series regression model. So we did the linear parameters, zero conditional mean of error in the previous video. Now, what we want is to have no perfect collinearity, and the reason is the same as we had with cross-sectional data. I actually have a video in the playlist where I prove why no perfect collinearity has to hold, like has to be an assumption. Basically, if we have one independent variable, like in this case, price, as a regression based on the other independent variable, which would be assets, if we substitute this into the regression line, which I did in that video, we can prove that we are missing the effect of one variable, because the regression, the sales, is going to be explained by one variable only, since one of them already accounts the effect of the other independent variable. So what we're having an unnecessary variable in the model in this case. So that's why this slope coefficient would not be interpreted correctly. That's the idea. Now, besides the no perfect collinearity, what we also need is homoscedasticity of the error term. So that means a constant variance of the error term. So over here, constant variance, let's call it that way, constant variance. That's homoscedasticity, but constant variance, you know, it's in like English, so we can understand it better. How we read it, or how we write it, is that the variance of the error term, the unexplained term at any point in time t, given any independent variable at any point in time. So xi, that means any independent variable, either the price of the product or the assets that we have in the company, or any other variable that we might have in the regression line, at any given time, so any year that we might think of, 2016, 15, 14, and so on, that variance of the error term must be equal to 0. So in other words, we do not want to have a relationship between the independent variable and the error term, because of the same reason we gave for cross-sectional data. We might be missing a certain variable that makes our regression have a different type of variance. So let's give it as an example over here with the picture. If we have our sales at time t, right, and over here we have the price at time t, well, if we have such a relationship, meaning that over here the price and sales, they have a positive relationship up to a point, but eventually the price has a very different effect on the sales, meaning sometimes sales are really high because of the price and the other times are really low. Well, how can we interpret such a thing? Because notice the variance is increasing with the price. So let me draw that. Over here we have a low variance of sales, so it's, you know, pretty much uniformly around the regression line. Over here, that variation of the dependent variable is becoming very high. Well, that means that for a given price, which is becoming very large, so over here the jeans are becoming really expensive, sometimes sales are really low, but sometimes sales are really high. How could we explain that? Well, maybe there is also the effect of the trend in fashion. So if the jeans that we're producing are trendy, then people are gonna pay for it even though they're expensive. So in that case, if the trend, let's call it 1, right, trendy, and 0 non-trendy. If we have a trendy fashion thing for those jeans, then people buy it, so sales are up. But if the trend is not for those jeans, it's 0 and they're expensive, people have no interest to buy it, so we would have low sales. So what we can see is that trend would be an omitted variable in the model, so we might suffer from the omitted variable bias. That would be just one thought, you know, one thesis. Like, I think it makes sense. So constant variance, and the last one would be covariance of the error terms must be 0, meaning we have no serial correlation. Let me write it in English first. No serial correlation. No serial correlation. And in math, because math is just translation of words, that means is covariance of the error term. So the error term at point t and any other point in time, let's call that um, must be equal to 0. And again, what this is telling us is that the variables in the model, the independent variables, are independent from each other. So to have a look over here, the price in 2017 is independent from the price in 2016. So we cannot say that if price goes up in 2017, it's gonna go up in 2018, and then it's gonna go up in 2019. Because by definition, that means that the price are dependent among each other across time. And if that is the case, notice what's going to happen to the regression. Again, let's draw it graphically to see that we're not going to have a normal graph. Like if we draw sales versus price, sales at time t and price at time t over here. Now, what's going to happen if price keeps increasing because they are dependent? So maybe, you know, there is regulation in the fashion industry that tells the companies to raise the price for jeans. You know, for instance, what's going to happen is that once price keeps increasing beyond a certain point, the sales are going to go up and up. So they will keep increasing. We're not going to have variation below the regression line. They're only going to go up. So the relationship is not going to be strictly linear anymore, because we're missing this effect, which happens because of the dependency between the prices. So over here, up till a certain point, the variation is going to be normal, but beyond a certain point, it's not normal anymore. So we have a sense of serial correlation. And what is serial correlation of the error terms? It means that if we have large errors in one period, so over here we have large errors, it's very likely that we're going to have large errors for the next period, and the next, and so on, and so on. Because across time, the price is going to keep increasing. So when we compare the actual sales, so the actual sales versus the sales that we predict, that difference is going to be pretty big, because this increase in the price is going to make our prediction less and less accurate across time. That would be the idea. So that's why we want this not to happen, meaning this covariance between the error terms must be equal to 0. So these are the 5 conditions. Hope it all makes sense, and we are done.